let me start from the very classical object that already, I don't know, appeared maybe, I don't know, 150, 170 years ago. It is called Steiner porism. I will discuss what does it mean. Actually, roughly speaking, porism means just a proposition, but archaic word for proposition. But I know only two theorems that using this porism, at the Steiner and the Penselet also, Penselet porism. But in both case, it is a statement about that there are infinitely many different positions. What is a Steiner position? Suppose we have two circles, like here that you have on the left, right? And you consider any circle and continue to subscribe circles that touch, say left one and both given circles. Yeah. Suppose it happens that we start from this circle. Suppose it happens that and the last one also touch tangent to this the first circle. The Steiner's chain it is called Steiner chain. Says that we can start from any circle. It doesn't matter for which circle. And we start and we have the same effect. Look at there. It is sent me by Hungarian mathematician Gabor Damazdi. Look at this nice picture. I like this one. Look at this. Yeah, we have. It's a very good idea. I mean, like, and you can subscribe it more and more and more. Yeah. Okay. So it is a theorem. Oh, by the way, it is a few words about the porism. It is that says that the definition from Wikipedia said that Steiner's that porism is exactly like nothing more than only just some proposition. Okay. Another interesting appeared similar this type theorem appeared in 1937, and Fejes Tóth considered three mutually tangent spheres, and he proved that in this case there exist 6 spheres which is tangent to neighbors, its neighbors, and also 3 mutually tangent given spheres. Here we have a picture. The red one, it is a sphere that it is like substitute 2 spheres, because we have 1 sphere outer and 2 inside, and we see this 6 tangent spheres. Yeah, that looks like more complicated, but both results are very simple. Let me very simple. I will just to explain. I will explain how to prove that. A few words about Soddy. Fejes Tóth. It is interesting personality because he's a Nobel Prize winner. He's Nobel Prize laureate. He got Nobel Prize in chemistry, and he published several geometric article papers. And moreover, one of the I will discuss it later. His extension of Descartes' theorem, and he wrote even a poem. It's called the Kiss Precise. Yeah, I even look at this the poem. It's interesting. Oh, by the way, he published this paper about hexlet in Nature. We can see that it is publication in Nature, the ball of integers and hexlet. Okay, just a second. Let me show the paper. This is my paper but let me explain how to prove it. Actually, it is a simple exercise. for high school students exercise how to prove both results. I mean, like about Steiner's porism as well as like Soddy hexlet. We know that from it is a geometry fact, it is not complicated. That if you have that the inversion, if you have two circles, non-overlapping, non-intersection circles, then there exists the inversion such that we'll obtain the inversion sends these two circles into concentric circles. So we have a concentric circles, right? And we have inversion. So if you have what does mean Steiner chain? That means we have the radii, this two radii such that we can subscribe n circles inside. And since position doesn't matter, you can rotate, right? That means if you return back, you will obtain this is the proof of theory. The main lemma is in this case is the following: that we have there's any non-overlapping circles can be the existing inversion such as send that them to the two concentric circles. Oops, sorry. What is this? How to prove the Soddy hexlet? It is another. It's again inversion. If we have two spheres in any dimensions, say S1 and S2, that are tangent, then we can use this tangent point. I mean this tangent point as center of the inversion. In this case, is send these two spheres into the two parallel plane, right? So we have a plane, and if we have a third one, say this one, the central, right? We have a center. We have this sphere, the third sphere, right? And other spheres, they touch this plane as well, these two planes as well as like the center sphere. That means they touch the equator of this sphere, as a sphere, right? So we have actually a kissing arrangement because we have exactly of the same. We have a center sphere, equator of the sphere, right? And equator of other spheres touch this sphere. In our case, it will be circle because in this three dimensions we have two parallel. The equator will be circle, and we have exactly 6 circles of the same radius that touch our central circle. So the proof also even almost direct. So what I'm going to do right now, I'm going to consider just a second. Yeah. I'm going to extend this too simple fact and this proof to consider generalization both results. We consider exactly two cases. Namely, we have a family of spheres, and suppose that first two they are tangent, or S1 and S2 do not have any common points. That is, then we have inversion such that in the first case it will be we consider the center of a tangent point, and the second case we consider when we do not have a common point, then we have the center to the inversion IT is inversion such that they to be S1 and S2 to be two concentric spheres. Yeah. So we know that this exists, and we obtain the following for the following question. If we have this two spheres, Then we have a touching. Then we have our other touch spheres becomes of the same radius. So it will reduce like above. We reduce our problem to the problem about touching about we have a sphere and the other spheres that touch the central sphere. For instance, we have 3 of them. Yeah, if we have 2, that means say we have 2 spheres in R3 non-intersecting spheres, right? In this case, we have 2 concentric spheres. So we have, in other words, we have a spheres of the same radii, of the same radius that touch the center of the central sphere, because all of them are the same radius. So we have a situation that we can reduce our problem to the spherical chords. Spherical chords, it is in other words, it is another possibility. We have you can consider the several definitions, but that's not spherical chords. The simple one, it is I mean to close to this workshop, we have a sphere and we consider unit sphere, right? And we consider spheres of the same radii that touches this central sphere. The touches of the central sphere. The main thing is that they have the same radii. So it is the touching spheres actually gives spherical psychod. In other words, there is 3 definitions. In other words, that means we have a packing by spherical caps, and the third definition, what we actually is a simple one. Let us consider spherical chord, spherical psychod. That means all points. We consider a set of points on the sphere such that are the distance at least psi. The angle geodetic distance or angle of distance is at least psi. So we have how it is related to packing by spherical caps. It will be diameter, right? If you put if you consider this half of psi, it will be radio spherical caps. It will be packing. The same thing. It is for 3 definition, but it is obviously the same. Some of them is known, well known, namely when we have a size pi over 3, 60 degrees. Radius is it is a distance is 60 degrees. It is a kissing numbers. In other words, we have a central sphere. It's to consider the maximal size of this chord. Its maximal arrangement is called the kissing arrangement, and the maximum number is non-overlapping unit spheres in the touch central unit sphere. It's called the kissing number. Okay. Now we can consider name theorem about that. Okay, I called it F kissing arrangement of spherical F kissing arrangement. Suppose we have any family F spheres, M spheres. I told you that first where first 2 are non-intersecting or tangent spheres. Then the theorem said that it's called another, and we are looking for spheres that touch all of us, all spheres in this family, and the theorem, the main theorem says the following. Let me just repeat it to it. For a given family F, the inversion T that defines a one-to-one correspondence between F kissing arrangements and spherical psi sub F chord. Since I've got it because I already discussed when you sent this when the consider inversion, they send this our family of Keating spheres to their to some spherical codes. Of course, there is some distance. We will consider later examples. So this is the main theorem, main object, our main object. That is can give us extensions of both theorems. I mean, like Steiner and Steiner.
Oleg, I have a question.
Yep.
So this kind of a F-kissing arrangement could be really loose, right? Like the two main spheres could be like very close to the same size, right? And then you'd have a bunch of little. The rest of them could be like very little spheres, sort of scattered in between, right?
Can you repeat? Sorry.
Yeah, I mean this kind of arrangement could be very loose. Like imagine your two spheres which touch everything else are almost the same size and concentric. Then you could have a bunch of little spheres kind of rolling around in between the shells. Is that right?
Yeah. It is. Yeah, I understand. Let me give you example, right? And after that, maybe it will be more clear because I give examples that exactly our goal. Of course, there is different situation. It's sometimes it is not clear because, of course, it not always exists. Even for in two-dimensional case, when we have two circles, right? It is actually there is some constraints for fraction. I mean, this to fraction of to radii because they have to this it is satisfied. It has to satisfy certain constraints, right? Certain question. Yeah. So that of course it is not like if you little bit change radii, it will be it is not clear. It even not exist. But okay. Let me first to try to extend, try to find analogs of Steiner porism to all dimensions. Let me just to the theorem is the following. Suppose we have a family of m spheres such that first two spheres are non-intersecting spheres. I mean, they have no common copoint. If a Steiner packing is formed from one starting sphere, then a Steiner packing is formed from any other starting packing. Then that also will be a Steiner packing formed from any other starting point. I mean, okay, in this case, you can imagine like two spheres, like in 3D, for instance, in 3 dimensions, in a space, right? And suppose we have one of them, right? And like something like then we touch all neighbors, right? And in this case, we can start from any other point. You can actually there is some actually this family Steiner packing actually you can use SO3 on the group of action of a group SO3. It can be rotated in different cases. Of course, on the change radii, but it's also interesting problem. I tried to describe all cases when we have sort of Steiner extension. Look, what we can do in this case. For instance, in 2 dimensions, we take any circle, and we touch another circle. Or we have 2 neighbors, right? We consider like 2 neighbors, and in one moment, this chain will be closed, right? What we can do in 3 dimensions. In 3 dimensions, actually, the greedy we have a choice because if we start from one sphere that touch to both, right? It is not clear. You can start from any 2. you can start from any two spheres, right? And after that, you can add a third one and from both sides. And sometimes it can be called a Steiner packet. But look, what happens if you have two and the third one is touching? Then the center of this, we have a triangle, right? Actually, they form, if you think about that, the Steiner packet form simplicial in general case. In this case, and the triangulation. That, I mean, it is a bit triangulation. The center of this spheres form a triangulation. So we have a very special configuration. I mean, well, that when we can use any greedy algorithm how to build this Steiner packet, and that is everything is known in this case. If you consider image on the image at the sphere packet. So we are looking for spherical codes such that the contact graph form triangulation. Yes, simplicial arrangement. There are only 5 cases. Here we have a list of all 5 cases. Number 1, of course, in the Steiner case, it's only for dimensional D. It works for any regular polygon because it's a polygon. Another family is that was also considered before. I mean, like classical, it's Soddy considered that, for instance. It is a regular D simplex for any D. Yeah, and I mean this centers form a tetrahedron in 3 dimensions, and the third case, it is a regular cross polytope. All this family exists for all of them, and two special cases, namely icosahedron, because it is triangulated, right? And the 600 cell, it is also regular polytope and 600 cell, because it also it will be this. It also form regular simplex. I mean, consists of regular simplexes. Yeah. So I just we have only 5 cases, and interesting question related to this 5 cases. It is an extension. It's another very classical question. It's called it's like a very old classical. It is called Descartes theorem. Descartes considered, you know, for and 60. It's even known year when he obtained this theorem. He considered 3 circles, and the question is what the relation to is. If you have 3 circles, mutually touching circles, the question is how to find for the 4th one. There are 2 cases, internal and external, that touch all of the 3 cases. How to find the radii? He considered what he considered it. Now considered it only k. That means the curvature. That means 1 divided by radius. And this nice formula. There is several different form of this formula, but this show how to find radius of the 4th circle, right? And the sign depends on the this touch externally or internally. Yeah, actually, this theorem was extended Gosset, maybe in 19th century, and Soddy he wrote about this poem, about exactly about this case, and so it is actually known for we have five cases, right? And for the case when we have 4, it is solved to found by Descartes and many years ago, right? And almost 400 years ago, and for the case 2 for simplex, it was solved by Soddy and Gosset. It may be someone else. There are some other actually. I don't remember some details about this solution, but and it remain only 3 cases from our list. 3 cases: cross polytope for ON, icosahedron, and the cis-Grande cell. The question is how to find. Definitely, there exist some formulas for that, and I believe some polynomial formula, and to find this extension of the Descartes method. Okay, now let me tell a few words about what does it mean Soddy hexlet. In this case, we have. Let us consider the same case what considered by Soddy. He considered in 3 dimension M 3 spheres and looking for position. Of course, you can consider it any M, right? Let M will be between in n dimensions when M be between 3 and n plus 2 spheres. And to do that, all of them, let us consider the case, his case, namely, that it will be exactly all of them will be not any, can be they can be because it actually not assume this theorem not assume that say third one mutually touch first 2, right? But let us consider his case. In this case, we can compute psi as a dot. It is the inverse cosine of 1 over m minus 1. Yeah, and the theorem says that in this case we obtain the existence it will be spherical code with this psi. This theorem set. It is just it's again like nothing pure because I just to compute what I did. I just compute this psi. There is interesting cases. The first interesting case, suppose we have n equals 3. The case 3 spheres. In this case, as we saw, we have two parallel planes, right? And the sphere inside, and all other spheres they have to have the same radius. Say, suppose this distance between these 2 parallel planes is 2, right? Then we have a unit spheres, and all other unit spheres is also it is also have to be unit spheres that touches. We have a kissing arrangement. So we have a kissing arrangement, and we can ask many questions. We can ask some question about this. How many, for instance, like for the Soddy case, what's the maximum number? What is the maximum number of this sphere, right? And this F kissing family contains. It is the answer is known. It's also known for only for a few cases, namely for we know for n equals 3, it is 6, right? It's obvious because we have a circle and 6 circles around that. The kissing number is known in dimension for n equals 4. It is kissing number in dimension 3, and the kissing number known in dimension 5 and 8. I mean, for n in dimension 4, that means n equals 5, and also cases 8 and 24. It is all complete list of kissing characters. But in dimension 4, actually, it is still not proven that it is unique. It's a big open problem that the kissing arrangement is unique. So we can say something about extension of Soddy hexlet in dimension 4 or in dimension 5, and we have a 3 mutually tangent spheres. But however, this arrangement is not. It is very interesting to prove that it's unique. So we have the same situation as before, but it is still not known. But in dimensions 8 and 24, kissing arrangement unique. I mean, the maximum kissing arrangement, it's we can say that it's also unique. It's E8, and Lich lattice gives us this uniqueness. And so we have interesting extension of Soddy hexlet. Okay, let me finish this part. I will be exactly 30 minutes, right? Almost exactly 30 minutes. I'm going to consider the second part, namely, okay, just let us fix. When we already reduced our question about this F kissing family that extend Steiner chain and Soddy hexlet, right? We reduced to the spherical code, and now let us. We can ask many problems. One problem is the simple problem is, okay, what can be the maximum number? What kind contact graph? What we can say about contact graph? What we can say it's in civil problem. Actually, we can find all answers when we consider spherical code. Let me look on the change to the second part. And now we consider packing of equal circles. And here we have several papers, our papers with Alexei Tarasov, and also we consider periodic packing when we found some strange situations that they exist maximum for seven circles periodic, right? We have the maximal packing is not unique. Yeah, it is. I still surprised how it can be happen, because in spherical case for some it is we cannot such a case. Okay, it's already defined several times in this workshop, and Karabes had a talk about that contact graph. But let me define it a little bit different way. Actually, it can be defined for any metric space, right? For any finite subset of metric space, we can define psi of x, that is the minimum distance between points in this subset. As a contact graph, the contact graph is a graph with vertices in x, such that edges are such that this distance between these points are exactly psi of x, exactly the minimum distance. So this guarantees that we have at least one edge, but no more, right? But however, of course, we are interested when we have as many edges as possible. This is the point. Now let me just it will not a lot of many definitions. We defined actually, for simplicity, you can imagine like sphere, right? Sphere and the point in the sphere, and all distances is just you can consider as you want. It can be just Euclidean or geodesic distance between points, angular distances between points. Okay, and first question, what we are going to do? Actually, we are looking for packing by circles of the same radius, right? radius. And so we can imagine circles on a sphere, right? And the first we have to consider, we cannot consider all of them. It is not interesting, right? We consider such locally rigid configurations. What does it mean, locally rigid configuration? In this case, that means, you know, when we consider as a point, right, as a set of center of these circles, right? We consider the points. Then there are no shift of a single vertex. What does mean single vertex? We cannot shift a point such that to increase distances. So we consider it only such configuration. It is called it's old from German mathematician from end of 40s. It's considered that, namely Schutte and van der Waarden published several papers about that, and the Fejes Tóth in his book, that by the way it's already translated into English, his beautiful book in 1953. Yeah, it's now available, and the Gabor Fejes Tóth and and Lode Kupperberg the translation of this book. Yeah, he has a special chapter, I don't remember, chapter 9, maybe chapter 8, when he considered this irreducible contact graph. I know that, it is, well, probably he doesn't like, I remember we discussed it, he doesn't like this name, irreducible, but this classic, I can do nothing with that because it is already considered. Yeah, and so irreducible contact graph means if our configuration such that we cannot shift any circle, because that means, you know, in a sphere in 3 dimensions, at the circle at least there are at least 3 touches circles. They cannot give a possibility. Like locally rigid, if you prefer this word. Yeah. Okay. There is some interesting properties. Properties as the following. Actually, first of all, if you consider contact graph, first of all, it is a planar graph because it's on a sphere, right? Any vertex has degree 0. 0 means, you know, it is we have circles, right? Some we have circles, and we can put circle inside. There are also such configurations such that, you know, it cannot be touched. It has to be, according to this definition, it has to be as far as possible from the other circles, other points. That is isolated. Isolated vertex 3, 4, and 5, or 5. We have only 5. 6 cannot be because some of angles, the regular triangle, equilateral triangle in a spherical case has more than 6. It is has more than 60 degrees, so it cannot be 6. Yeah, and there are some other for n greater than 10. Actually, there are cases that contains isolated vertex. Maybe I have some example. Yeah. It also some other geometric properties, but for when n is big enough. Actually, it is considered first. Of course, Schutte and van der Waarden, when they proved the Kissing number problem in 3 dimensions, they considered, and before they considered Tammes problem, it is another paper in 1951. They considered this graph, but first who tried to classify not only optimal, not only the main optimal case, maximum case, maximum arrangement. It was Ludwig Danzer in his habilitation. This habilitation means 2nd degree that not exists here, but in Germany and other European countries they exist, the 2nd degree, doctoral degree. And he, it is, by the way, it was translated. It was 1963 in 80s. It was translated into English. Oh, yeah, it's large paper, like 100 page. Bad written, by the way. I spent one summer to understand all details of this proof. I cannot say that it was useful, but anyway, you know, I just to feel I just to try to understand this technique. Maybe it helped me. It helped me a little bit. Okay, he considered not any irreducible. He added also one more constraint, namely, he also gives this. He calls this D flip. I call this D flip, Danzer flip. That means, you know, suppose we have. Oops, sorry. Yeah. Suppose we have our graph, right, and we have contact graph on the sphere, right, and suppose we have we take a vertex and look at this diagonal, and we can flip it x to x prime. He also allows it. If in the case, only in the case, then the distance from x prime is greater than our given distance. We have already a distance. You know what the point is? It is a graph such that all edges have the same length. That is the main point, because we have all of them, you know, taken by this is content graph, right? And so in this case, he allow it also can be rigid from a Danzer point of view. It also not allows this operation. It is just, of course, it will be much less. I will show numbers a little bit later. We will see how what do we have here. Yeah, it is his habilitation script by Danzer in 1963, and he gave a classification of all D-irreducible graphs between 6 and 10, and his PhD. Let us see his family. The first case we consider 6. We have the maximum. It's screw. Yeah, we have this triangular, right? This we have two triangles. This configurates this optimal triangulation, and this triangulation with the maximum distance, minimum distance. But this one is a family. It is a family, one parametric family. Yeah. It is like just okay. For one side of this family, we have a triangular prism. It is with a minimum length of, and on the other side we have a maximum. It will be this one. I mean the left one. Yeah, we have also two families left for 7 points, and one family it is a parametric. And for 8 points, he found 3 cases. Yeah, and moreover, look, 8 points. We have the optimum. It's called screw cube, right? Screw cube. When we have it for squares, like rotate like this one, right? In this case, but also the maximum is for 8 points is a screw cube, this one. The minimum is a cube. The cube is the worst case. I mean, because in this case it will be minimum distances. But look at this. This is a 2 parametric family actually, not only one parametric, but a 2 parametric. Just can you imagine? Just let me just explain what this picture. Suppose we have. Let us consider two spheres, like the situation what we have as Steiner, right? And try to find some arrangement of spheres, right? Such that rigid. I mean rigid situation. I mean this kissing between them, right? But suppose we have a balloon that can be increased or decreased radii, right? In this case, this family actually not only, of course, it can be rotated as a solid, right? but however, it also can be increased or decreased simultaneously radii. It will be interesting family, right? With two in this case, in the case, eight spheres between two that touch to them, you know, we have even two parametric. Here we have three cases, Danzer cases for 9 points and 10, right? If I remember, 10, right? For 10. What we did with Alexei Tarasov, we actually decided to consider a general case, just irreducible graphs. It's also interesting from practical point of view, because we discussed with material scientists. They say, oh, it is interesting case because when we have Danzer, actually it is a little bit artificial because they have not in nature. But if you have some molecule, right? If you have one sphere and around other, right, of the same radii, it is interesting to consider configurations. So we continue that. In the first case, instead of 3, we added this one. We have the 3 Danzer found by Danzer, and we have found third one. Right here, we have in radians. We have actually the family at the minimum and maximum D. Actually, we not consider it like it is we just to consider we found minimum and maximum. You can see here. So what is interesting here? We have a pentagon. So it is at a y. So it is not allowed by Danzer because there is some flip that give. I mean, like, so it is one more. For 9, we have already 10, 3 times more than Danzer has. Right here we have all of them. And for 10, we have 30, right? We have 30, yeah. We have 30. Danzer has sorry, yeah. And Danzer has 10, as I remember, 3 times more actually. And for 11, Danzer not considered the case of 11. We have, I don't remember how many, 30 something, 39. Yeah. So if we can, it is very complicated to continue this search because it took maybe 1 year. I mean, like even for 11, and I have a little bit doubt about last one because I checked very carefully first, I mean, up to 10, and for 11 it was so many. It is it took so many 10. They said, okay, one moment we said, okay, let's stop because we couldn't find any other family. Right? But for 10, it's one interesting conjecture. I discussed this also with Bob, with Connolly, and with many other. If you look at this conjecture, we call this 2n-2 conjecture. If you look at the maximum with the maximum H graphs, I mean with the maximum distance graph, length graph, we have always they have 2n-, with n vertices, you have at least 2n-2. There are some cases like for 7 probably. I remember for 13 we have exactly 2n-2. But we cannot prove it. The conjecture is it follows from dimensions. Also, if you look at the dimension of question, that it has to be like 2n-2, but we cannot prove it. It is very interesting to prove this conjecture because otherwise, maybe I don't know. It is it can be actually maybe to exist such configuration. I forgot how Bob called that. So can you imagine? Suppose we have this point of the same distance, right? And we can move it such that this graph such that simultaneously, such that we preserve the distances. He has some special flex or something. special is here. I cannot see him, right? But it is this conjecture, particular this conjecture actually contradicts this, the existence of this case. Okay, anyway, it is a well-known problem. It's called the Tammes problem. The Tammes problem asks actually for exactly what we consider for a given n to find such a configuration such that it is has a maximum minimum distance. Here we can see another rotation. How must n congruent non-overlapping spherical caps be packed on the surface of a unit sphere such so that the angular diameter of spherical caps will be as great as possible. It is the same what we consider. We have like two stars means exactly the solution of Tammes problem. Actually, Tammes problem is now solved only for several cases, namely Fejes Tóth, Fejes Tóth in 1943. He has a Fejes Tóth bound, so-called, and gives solution for 3, 4, 6, 12. Schutter van der Waarden considered 5, 7, 8, 9. By the way, 5 in the case 5, it is also for high school. So even one I saw that in some German Olympiad, mathematical Olympiad for high schoolers to solve the case 5. Case 10, 10, 11, it is a Danzer in his work in 1963, what I mentioned already. A very interesting case 11. 11 is of course for 12. It is a icosahedron, regular icosahedron. But 11, nothing better than we can remove one of vertices and we obtain the optimal configuration for n equals 11. Yeah, and there was a separate case. It was even before, because it is a very symmetric configuration proved by, actually he extended, proved by Robinson, and he extended some method by Fejes Tóth method. So it is these methods. I mean, Danzer and Schutter van der Waarden, all of them based on contact graph. This main technique is irreducible contact graphs, nothing more. It's a more or less simple geometry. But Fejes Tóth, he considered he has some actually inequality that works for when actually it is for triangular when we have a triangulation, they form triangulation. I mean, this vertices of this optimal and for high, it is. And Robinson also considered when we have a triangle and squares. And we actually solved the problem, this problem for Tammes problem for 13 and 14, but we enumerate by enumerating different graphs. For instance, so this is status of this conjecture, and the 15 is the first open question. Actually, let me just almost finish. Just to show examples. This is example. This is solution of the Tammes problem for 13 points. To prove that we consider it about 100 million graphs. I remember. Actually, I remember my first. I said when we discussed with Alexei, it was maybe 10 years ago, more than 10 years ago. Yeah, we sit here in Texas, and I told him, let us use. I'm familiar with this technique. I mean, this Del-Sat method and linear programming. Let us use this one. It may be and also appeared already at that time already semi-definite programming. I mean, let us use this. But he's for that he has to spend, I don't know, maybe several weeks or several months, I don't know, to study, to understand what does it mean, this method. And he said, okay, and he started to he said, let us to enumerate all cases. I said, okay, why not? Maybe we'll have with this. I show you this constraints for graphs, right? Okay, maybe there are a few hundred. We'll look at them, we look at these cases, and and prove that almost by hand. But when we received 100 billion, 100 million cases, it was upset. But however, 99% after it is generate, there is some generating these graphs, but I remember that it will be eliminated all cases, 99% of cases eliminated during next 2 hours. And other also, but we spent about 1 week computations for certain when to eliminate like some bad cases for other. It depends on method, because like especially when we have a pentagons, it will take a lot of time because with some division. It depends on the method, because we use a method. We use only linear programming, nothing more. Okay, this is a case 13, and for case 14 it's already we consider it 1 billion. It's about 1 billion cases graphs. We consider it, and to prove that this configuration is optimal, and also, but no way, I mean, to go for 15 and using that. We need something smart, something new, some new ideas. Because in this case, and one of them, you know, to at least if you have sort of this conjecture, 2n-2 conjecture, because to show that we have at least 2n-2 edges, right? It helps a lot. Otherwise, it will be, I don't know, it's impossible. I expect for the 15 like 10 billions. It was already impossible. It took for 14, it took a little bit less than 1 year. No, of course, you know, not all computations, but we with some improve something can try to reduce some cases, eliminate some cases before. Yeah. Okay. Probably. Let me stop this case. Oh, by the way, can I have 2 minutes? Yeah. Okay. Thank you. It's one more problem also about that one. It was also, I mean, you can see, if you want, you can consider it like the case of 2 spheres, right? And the spheres one of the interesting question related to contacts. It's already Karol basically already presented something, but not for spherical case. This question very old, and there are several papers. That one of interesting papers published by Fejes Tóth. He considered spherical contact numbers, because we have what we have a spherical caps, right? The question is, in my language, we have to find maximum edges, right? But he defined also for a given n. We can define for a given distance. We can define k sub n of t. It is a contact number, maximum kissing contact number on n spherical caps with diameter d. Yeah. And that is interesting. Robinson, I already mentioned his name, in 1969, and the Fejes Tóth solved the problem for cases we can see here cases to find the maximum 2, 3, 6, and so on, and 60 and 120. The reason is because in this case, we have it depends on diameter d, but we have a kissing number. It depends on diameter d. It can be the first case is 3, right? Between 3, 4, and 5. It cannot be greater than 5 actually. And they consider it all cases then when all the maximum configuration has always has a maximum number of kissing number. I mean local kissing number. In this case, they count it. The remain case you can see here, the remain case we solved with Tarasor, just how solved, because we have already classification. So we found all other cases for 5, 7, 10, and 11. 11 we know maximum configuration. Surprisingly, in case 10, this number is 21, but the time resolution of Tammes problem gives only 20. This graph that give you maximum contacts, right, is not irreducible. I explained how it looks like. Take icosahedron and remove two neighbors, two vertices, and vertices we obtain 10 vertices give us best solution. So that are two different problems. I mean, the Tammes problem and the maximum contacts. I mean, like contact number for a given number of for a given number of vertices on a sphere, right? Circles on a sphere to find the contact number. So that is interesting, and I believe it is a more simple problem if you compare with the Tammes problem, because also we can enumerate, but in this case we actually not much geometry, because we are looking only for contact. Yeah, several also interesting, some asymptotic for this maximum contact, but this I believe it is interesting problem and can be considered. Okay, thank you.
Thank you for that very interesting talk. Let's thank our speaker. And I think we have time for a couple of questions.
Oleg, this is Karo speaking. Can you hear me?
Yes.
Yeah, I just have, you had a lot of open questions in your talk. I just want to add an additional one, if it is open. And this is about the first topic on Steiner porism. So if it appears that it characterizes Euclidean norm, and so the question is, what happens if you replace the Euclidean norm by some other norm? One could think of a norm very close to the Euclidean one, and you could, ask for existence of Steiner sequence for a given norm. So what I'm trying to ask, I mean, it appears that that first topic falls in the close neighborhood of Schramm's theorem about generalizing Kolb-Andreev certain theorem. And so it feels like, a problem that could be considered. Have you considered that, or has anyone worked on this?
What, maybe you're familiar. Do you remember, like Conrad? You remember him, right? Swainpool.
Yeah.
He considered some. I'm not sure, but he considered something like that. Not.
Mm-hmm.
Look at his papers. Right.
But your feeling is what? So do you think Steiner porism characterizes Euclidean norm?
Steiner porism characterizes conformal map. Actually, it is a hyperbolic. It is a fact from hyperbolic geometry, by the way, not Euclidean.
Yeah.
Yeah. It is for Euclidean region, right? Because if you what about this Steiner porism? Because if you have, since it is invariant of on the inversion, right? Conformal maps. So we have that exactly what we have. What we have. It also the same for high dimensions. If you look at the other, so it is hyperbolic geometry, not Euclidean. If you, for Euclidean, actually, it is not clear what does it. It is only particular case we have when we have two concentric spheres, right? It's only one case in Euclidean, because it's preserved for distances. Metric.
Yeah, the other question is about the last topic. Have you tried to extend your investigations to higher dimensional spherical spaces about the maximum contact?
Yeah, it is interesting question. It is It is very hard, actually.
Mhm.
It is very hard. I always thought about that. Not graphs to consider complex, right? To consider complex. You know, even still, up to I don't know how many years attempts, and the kissing arrangement in 4 dimensions still open. That means we have a 3-dimensional case because we have a 3-dimensional sphere, right? And spherical 3-dimensional sphere in 4-dimensional case, in 4-dimensional space, right? And in this case, it will be we have some poly. It will be complex. Some not graph. I mean, we have also faces. I remember that I tried to do that, but even for the case 9 points, the problem is still open. To find in 4 dimensions, to find the optimal configuration, solution of the Tammes problem with 9 points.
Mhm.
The answer is known, the conjecture is known, and Henry Cohen has a conjecture many years ago. It is more or less obvious. Look, 1 point, we have 1 point on the North Pole. After that, we have a tetrahedron, regular tetrahedron, at the same distance, and we have another regular tetrahedron and the last parallel, right? And so it is. You can compute everything geometry. It is not open. Very natural. What you to use this approach to extend this contact graph into this contact complex. I don't know how to call that. Contact complex, right? And in this case is known. I describe it. Actually, it is if you consider like as a convex hull of this sphere, we have a point on the sphere, right? We have a convex hull. We have a polytope, actually, 4-dimensional polytope, right? Yeah, it is extremely interesting. Even if you can say something about this, I mean, like about this technique, to try to first to solve this problem. 9 points. I recently received some submitted the paper, but it is there are gaps of that. Several people also claim that they solve the problem, 9-point problem, but however it is still open. Yeah.
Thank you.
Yeah. Yes.
So
Richard, are you here?
yeah. So,
Yeah,
so
yes.
I wanted to say something about it. So the Poncelet porism and the Steiner porism are actually pretty different because the Poncelet porism is quite harder to prove. You know, it doesn't follow from just the symmetries of the group.
Yeah.
Have you thought about, like, you know, projective analogs of these higher dimensional configurations?
I never think about that. I never thought about that because I know that was a Poncelet, but I never thought about that. Oh, by the way, it is actually what is interesting. We can consider projective version of this everything there. I skip this part. I mean, it's not related to Poncelet conjecture. It's not related. I just for Poncelet porism. What is it? Also, we can put together. We can assume also that we have some on the projective space. The same thing in the projective space, but not much known about that, right?
Like, I mean, you could have like ellipsoids rather than spheres, for example, and you could ask. I mean, there's some theory of like.
I knew nothing about that.
Okay. Anyway, all right. Never mind. But there's
no. I know that it is interesting.
There's like a theory of billiards on like quadrant surfaces and things like that. And
it is, yeah. I believe it is some heavy algebraic.
Yeah, right.
Real algebraic geometry. It is not
right.
like because it is no. Yeah, it is interesting, of course, but it is not much known about that.
Yeah, different subject.